All right. Hello, everyone, and welcome back to Calculus. Today, we are going to be talking about optimization, which means sort of finding optimal ways to create amounts. In other words, finding maxes and minimums is really what optimization is about. Um, so our goal is we're going to use first and second derivative tests, right? Because that gave us ways to find relative maxes and mins. And in order to maximize or minimize real world quantities. So really all this is today is going to be applying first and second derivative tests to real world situations. And turns out that we can kind of create some fun and interesting problems that are very much sort of applicable to a real world situations using just the first and second derivative tests. So because of the nature of these problems, we're often going to need two steps. So we're going to sort of create a formula and really creating a picture that helps us create the formula that models the real world quantity. And then we're going to apply the first or the second derivative tests and sort of interpret it. Okay, so for example, we're going to look at a farmer who has 500 square feet of fencing. Square feet. He has 500 feet of fencing, goodness gracious, that he's wanting to use in order to create two rectangular regions that share a side. So pens for two different animals or something. And the question that he's trying to figure out is what dimensions he should use in order to maximize the total area of his fenced-in regions. So first and foremost, let's draw a picture. Sorry, not 500 square feet again. First and foremost, let's draw a picture of what this problem is telling us. So problem says that he wants to build his fencing somehow like this. So we're going to have two different rectangular regions that share a side. Okay. And we're wanting to maximize the total area of the fenced-in regions. Okay. All right, interesting. So I guess let's just go ahead and start giving names to things and seeing if we can't figure out sort of a good equation for the total area of the fenced-in region. Okay, so let's see. If I just give a name to this side length and call that X, and let's see this side length and call it Y, then of course I know that area equals X times Y. That's too many variables to do the first or the second derivative test, right? Like we didn't have multiple variables involved when they did the first or the second derivative test. So I really would like to get my area just in terms of one variable and not two. So let's see if we can use the other information that's in our problem. So we were told that in total we have 500 feet of fencing. Okay. So that 500 feet becomes 2 copies of Y and 3 copies of X. So I can translate that into a new equation that I'm going to use to sort of simplify down this area equation. So that's why I'm going to write it this way. But okay, so I know that 500 equals 3x plus 2y. So I can now use this to solve for y in terms of x, and then I could like replace my y in my area formula with just x's. Awesome. Okay, so that's what we're going to do. So we're going to solve for y. So 500 minus 3x equals 2y. So y, I know, is going to be equal to 500 minus 3x over 2. Okay, so now my area formula, I'm going to substitute that in. So my area formula is really going to be x times y was 500 minus 3x over 2. That's awesome. Now I have my area formula in terms of just one variable. Think about area as a formula of x. And that's awesome because now I can apply my first or second derivative test. So now I have a function that I can go ahead, I have tools to find maximums and minimums with. Okay, so that is sort of how we find our area formula. And then after this, we are now really just looking at a first derivative or second derivative test question. Okay, so let me delete out the parts that I don't need now. So end of day, really what I care about is maximizing this formula. Okay, so let's go ahead and simplify that down a little bit. I'm looking at 250x minus 3/2 x squared. Okay. And it's also worth noting that, so what is our goal right now? We'll use the first derivative test. You could use the second derivative test, doesn't matter which. But we're going to use the first derivative test to maximize area, right? We want to find relative maximums. And anytime we're working in these sort of real world quantity problems, you're usually going to be working with a closed interval. So if we think back to our problem, we have 500 feet of fencing. So it makes sense that X was one of our side lengths. Right, we absolute maximum, we would make this side length be 0. That's not reasonable, but like absolute maximum way to have the largest X's. And so that would mean the maximum that X could be is going to be 500 over 3, because we have 3 copies of X that make up the full 500 feet of fencing. Or we could minimize X by making that side length be 0. Again, not something that we're going to want to do, but that is kind of like the full realm of X values that like make any amount of sense in this problem. And so we're maximizing A of X on that closed interval from 0 up to 500 over 3. Okay, so now this is just a first derivative test question. So first derivative test says that I need to look at the first derivative, which is 250 minus 3x. And I need to create a number line. Except, oh, I already did something silly. My number line isn't the full number line, right? It's just from 0 up to 500 over 3. And so then I need to, so first derivative test, first thing I need to do is I need to find the zeros of A prime. So this would equal 0 when X is 250 thirds. So that's going to be halfway through here. So 250 thirds, A prime equals 0. And then I can do my test points. So if I test like X equals 50, then A prime would be 250 minus 150. So that's going to be positive. If I test something in this region, let's say testing X equals 100, then I have 250 minus 300. So A prime is going to be negative in that region. Okay, so now we pause and we think about what the first derivative test tells us about these things. So we had F prime being positive before X equals 250 over 3, and then it becomes negative. And so first derivative tells us that this X value is going to be a relative maximum. So by the first derivative test, X equals 250 over 3 is going to be a relative max. Okay. But don't forget, when we were looking at doing the first derivative test on, goodness gracious, when we do first derivative test on closed intervals, we always have to be careful and think back about our endpoints. And so what we're going to do now is we're going to make sure that that really is where the maximum area happens by checking our endpoints. So what I mean, so the max area will happen at x equals 250 over 3 or at one of the endpoints, x equals 0 or x equals 500 over 3, right? Because we can have endpoints that maximize our function as well. And so the idea is you need to go through and test all of these in the area formula. So go back and calculate area at 0. Turns out that is 0. Plug in 250 over 3 to the area formula, which is, let's see, I think that's going to be so 250 over 3 times 500 minus 250 over 2. Okay. So whatever that amount is, it's going to be a positive number. So this is already bigger than what happened at x equals 0. So we can already say that x equals 0 is not where the maximum is going to happen. Then I'm running out of space because these are such large problems. But we can also test or we also need to plug in our last endpoint, which was 500 over 3. So the area at 500 over 3 is also going to end up being 0. So thus, because those were our 3 options for the maximizing area, we just choose the biggest number that we got from plugging in all those options. So the maximal area is going to be this 250 over 3 times 500 minus 250 over 2. That's going to be the maximum area that we can find. Coming from a side length of x being 250 over 3. So if your farmer is trying to maximize his area, he's going to make each of these sides be 250 over 3 feet. And then you'll have the remaining 250 feet. You're going to divide that on each side. So you'll have 125 by 125, and then 250 over 3, 250 over 3, 250 over 3. That is how your farmer would maximize the area of his region. So yes, these are rather large, rather long problems. You've got to sort of set up your equation, set up your situation, get it down to a single variable, and then apply the full first derivative test to your problem, or the full second derivative test to your problem, being careful about your endpoints. So lots of things to be careful of and be mindful of as you're going through and doing these problems. Okay, so let's do a second example. So we're wanting to construct a box whose base is a square and whose total volume is 15 cubic feet. The material used to build the top and the bottom of the box is going to cost $8 per square foot. And the material used to build the sides is going to be a bit cheaper. We're going to have that be some material that costs $6 per square foot. The question is, what dimension should we use to minimize the cost to build the full box? Okay, so we're minimizing cost. So that's going to be the important equation. And so let's sort of start by figuring out that equation, maybe in terms of multiple variables, and then we'll cut down to a single variable. Okay, so we're told that our box is going to have a square base. That we're going to have an x by x base. And then we're going to have some height that might be a different number, right? So let's make that height be y. Okay. All right, so this is our box that we're looking at. Okay, so the cost to build this box is apparently, so for our top and our bottom, those are going to cost $8 per square foot. And the square footage on that, the top and the bottom are both just x by x. So the top cost is going to be 8x squared plus 8x squared for the bottom cost. So cost of the top side, cost of the bottom side. And then we need to add in the cost of all of the sort of vertical sides. And let's see, each of those seem to be x by y. So each of them have an area of x times y. And the cost for the material is $6 per square foot. So we'll have 6xy is the cost of each side. So cost of each vertical side times there are 4 sides. 4 vertical sides, right? So my total cost is going to be 8x squared plus 8x squared plus 24x times y. Okay, cool. So that is my cost equation. This is the thing that I'm going to try to minimize. But again, I want to get things in terms of just one variable, not 2 variables. So I want to maybe be able to replace this y by something in terms of x. And so that is where we're going to go back to our other information that we were given and try to solve that for, try to use that to solve for y in terms of x. So the other information that we were given that we haven't really taken into account is that the volume of our box should be 15 cubic feet. And the volume of the box we know is x times y. So I know that 15 should equal x squared y. In other words, y is going to be 15 over x squared. And that is sort of the other information that we were given in our problem. So now we can plug that into our cost equation and figure out that, okay, so we had 16x squared plus 24x times y. Now I know that y is 15 over x squared. And so really, my cost equation based on a base length of x is going to be 16x squared plus 24 times 15. 24 times, so 6 times 60, so 360 over x. Okay, so step number 1 is done. We have found that if I set my problem up like this, I have a base side of x and a height of y, then this is what my cost equation gets me. Okay. So now the goal is to minimize my cost. So minimize C of x And again, there's certain things that will and will not make sense here. So in particular, since x is the length of something, it's going to make sense that our minimum length is going to be 0. But technically, by like squishing down y, going closer and closer to 0, I could make a box with a volume of 15 cubic feet by expanding x infinitely off. So really, I don't have much of a top endpoint. X could technically go off to infinity, but I do have a lower endpoint to be mindful of on this problem. Okay, so that is what I'm doing now. I'm just minimizing this equation on this interval. Okay, so that is a first derivative or a second derivative test question. Let's go ahead and do a first derivative test again. So first derivative test says that I need c prime of x. So I should be looking at 32x minus 360 over x squared. Got that by thinking of 360 over x as 360 times 1 over x, or 360 times x to the minus 1. And so we can use power rule to find the derivative of that. Okay, and so to set up my number line, again, my minimum is going to be at x equals 0, then we're going to go off to infinity. And then I do want to think about what x value could make this equal 0. So c prime of x would equal 0 when this is true. Okay, so in other words, by adding 360 over x squared to both sides, I would have that be true. So in other words, 360 would equal 32x cubed. So x is going to be the cube root of 360 divided by 32 when you go ahead and solve that all out. So that is the one point that I want to add on to my number line. Cube root of 360 divided by 32. Okay. So now I just need to do my test points. I'm gonna test x equals 1. And there I would have c prime equals 32 times 1 minus 360 over 1. So that's going to be negative. And then I'll test anything that's after this cube root of 360 over 32, cube root of 10-ish. Okay, so I could do 10 would be a perfectly fine test point. So c prime of 10 is going to be 32 times 10, so 320 minus 360 over 100, so minus just 3.6. So we're going to be positive in that region. Okay. So this is my sign chart for c prime of x. So now, last thing is go back and interpreting that and being careful about our endpoints, checking our endpoints. So, okay, so we have f prime is negative, then positive. So if we remember, that means we're decreasing, then increasing. So by the first derivative test, x equals cube root of 360 over 32 will yield a minimum or a relative minimum. We also need to check our endpoints. And so this is where we are going to check x equals 0. And by check, I mean, look at the cost associated to each of these things and really choose the minimum cost between these two choices. So, i.e., we need to calculate the cost at 0 and the cost at this cube root of 360 over 32. And then we will just choose whichever x value truly gives us the minimum cost. Well, turns out cost at 0 is not defined. Again, remember we're looking at cost of 0, not c prime. But this 360 over x, this just doesn't even make sense. So we actually can't even really think about our endpoint. And that makes sense. A box with a length of 0 is not actually a box we want to build, right? So the minimum cost is really going to be given by plugging in the cube root of 360 over 32. And so that minimum cost is going to be 16 times cube root of 360 over 32 squared plus 360 divided by that cube root. And so what we get at the end of the day, is because these were the two options for where cost could be minimized, we get to choose the best one, which is this second point that we checked. So the minimal cost is going to be that amount coming from a box with base side lengths, which was our x value, right? So base side lengths of this cube root of 360 over 32. Cool. So that is how we would minimize the cost of building a box that needed to have this particular volume and these particular materials for the tops, bottoms, and sides. All right. Last problem, I promise. But I want y'all to go ahead and try an example of this yourselves. So you're given a piece of cardboard that measures 2 feet by 3 foot, and you're planning to cut out a square at the end of, or at each of the corners, and then fold it up into a box. So you're given this piece of cardboard that is 2 feet by 3 feet. And again, you're just going to sort of, your goal is you're going to like cut the same square from each of the corners. And yes, squares. And then you would fold it up. And so you'll have a box where each of these like you're going to fold along these green cuts. So that's where your length up is going to be. That's like the upper sides of your boxes. Okay. Okay, so you create a open box that stands up by cutting out these squares and then just folding along those squares. Okay, so that is sort of your starting point. And then what you're trying to do is you're going to try to maximize your volume. So make whatever square cuts make the most sense in order to maximize your volume. Okay, so go ahead and pause here and try this problem. All right, so either way, if you did first or second derivative test, you should figure out that you want to cut squares with side lengths of 0.39 feet each. So each of these side lengths should be 0.39 feet on your cuts, and that's going to maximize your volume. All right, y'all, you did fantastic, and look forward to seeing you later.